Alrighty, let's see what we got here. It's going to be a problem I previously solved that's hard. Maximum running time of n computers. You have n computers given the integer n and zero index array batteries where the ith battery can run a computer batteries at I in minutes. You're interested in running all n computers simultaneously using the given batteries. Initially, you can insert at most one battery into each computer. After that, and at any integer time moment, you can remove a battery from the computer and insert another battery any number of times. The inserted battery can be a totally new battery or a battery from another computer. You may assume that removing and inserting the process takes no time. Note the batteries cannot be recharged. Return the maximum number of minutes you can run all n computers. So, number of computers. Each computer needs to be hooked up to a battery. The battery loses energy. Kind of discrete time. So there's two computers here. 3 batteries with charge 333. So here you're plugging in arbitrarily to the batteries to those computers. They each charge for 2 minutes. And then you switch one computer to the last battery, and that will allow you to run another 2 minutes, so it's a total of 4 minutes. Okay. Alright. I think I understand this. I mean, I understood it once before. I guess I'm understanding it again. 4 batteries, each with 1 charge, 2 computers. Obviously, it's going to be 2 minutes each. Or 2 minutes able to charge both. Okay. I wonder if this was a previous daily problem that I finished, or was this part of some sort of other challenge. In any case, what's the idea here? The idea here is that a greedy approach to using the batteries wouldn't work because if you just like assign a computer to a battery and use it completely, then you might end up with another battery whose charge is capable of being used on the computers, but not on multiple computers at the same time. So when would you need to switch batteries to prevent that? Total number of time, total time. Don't think this is binary search. Like, I don't think I can just guess a time and see, and well, can I guess the time and see if all the computers can be maintained for that time period? I don't think so, because the actual choice of which batteries to charge what computer is at what times and when to switch batteries isn't really immediately known, or what's the best way of doing that isn't immediately known. So I don't think it's binary search for the best time. Feels like it could be a heap, or it could be a sort. I think you probably want to sort by the battery length first. I mean, sort by battery length first. So if you had, let's say, let's say the battery charges were 1, 2, 3, 4, and let's say you had 3 batteries. I think you probably would want to. Is it the case that you want to always switch out as much as possible? So it's the sum of the values here is 4 or 10. Sum of the values here is 10. And there's 3 batteries, so the best you can hope for is 3. Maintain time 3, because then that requires 3 times 3, which is 9 charge. So the question is, can you somehow, what is the ordering of it? Well, if your goal is 4, or if your goal is to maintain 3 at all times, 4 doesn't really matter, right? Because however you allocate the 4 is never going to allow you to fully use the 4 charge there. So it's more of how you allocate the remaining things. So obviously here this is going to be 3. You do a 1, 2 to get 3, and then you do 3 of the 4 to get the other 3, so then all 3 is charged. And if there's 4 computers and 4 batteries, then I don't think it matters however you want to allocate it. It's always going to be the minimum. I guess the number of batteries has to be at least the number of computers. Number of batteries is the least number of computers. So I think maybe I can do the trivial case right here. If the number of batteries is equal to the number of computers, then this is going to return the minimum of the batteries, minimum charge. And then the max time would be like the sum of all the charges divided by the number of computers. Like you're never going to be able to beat that. So let's try something more intermediate. So something like that, 5. This is still probably too simple maybe. Here ideally you get 5 time, so maybe 5 to one computer, 1, 4 to another computer, 2, 3 to another computer, so that gives you 5. This is just too simple. So here the sum is 15, divided by 4 is 3.75, so the best you can get is 3. So like 3, 3, 3, and 1, 2. Okay, I think maybe the example one was actually more tricky than this. Okay, so the batteries is 3, 3, 3, 2. So here ideally you get 4. So your max time is actually higher than the highest battery charge. And it's not possible for you to say that max time is all done by one charge, by one battery. So you can't just do 3, 3, run out, and then try and have both computers use this last 3 at the same time. So what's the way to do this? So max time is 4. 9 divided by 2, 4.5. So obviously start by assigning 3 and 3. That's all you can do. After 1 times, now 2, 2, and 3. When do you have to switch? When do you have to switch? Max time is 3. No, max time is 4. 4. That's the logic. So after time 1, it's 2, 2, 3. And then in theory you could switch here. In theory you could switch, if your goal is to have 4, you could switch from this 2 to this 3 and get 4. But if you don't know that you're able to get to the max time, then is that reasonable? I guess you always want to switch. I guess I guess it's never wrong to switch to a higher charge battery, right? It's never wrong to switch to a higher charge battery. Yeah. So it'd be wrong. When is it wrong to not switch? Wow. Okay. So time 2. If you don't switch, then it's now 1, 1, 3. Time 3. If you don't switch now, it's 0, 0, 3. And then you're stuck. If you switch after time 1, then you get then you get 2, like maybe 1, 2, 2. Yeah, 1, 2, 2. Keep the same battery on the first computer, so it becomes a 1 charge. And then switch the computer to the third battery. And here, obviously, you wouldn't need to switch, right? So now it becomes 0, 1, 2, or 0, 2, 1. And then like 0, 0, 1. You have 1 spare. That would be a lot of switching. Or if you're always trying to switch from battery to another battery that's better or more charged, then that'd be like an analog B operation, maybe? Yep, and computers that you're trying to find the maximum battery for. Yeah, it's not for me. That's really slow. I wonder. I wonder. I think I first almost assuredly want to sort. Doesn't matter the order. I'm pretty. Yeah. What's that one? I'm thinking about like in kind of the most general, or thinking about like kind of summation of values. So here, right, let's say n is equal to 4. Is it possible to do a guess? Guess you guess the max time somehow. So in theory here, sum of 1 to 10 is 55, I think. 1 plus 10 is 11. 11 times 5 pairs, 55. 55 divided by 4 is 13.75. So the max time is 13. 13. So if I guess 13, then I guess 13, then I would try 10. I pair 10 with like 4, 10 with 3, 10 with 3, 9 with 4. Hmm. Pair 10 with 4. No, pair 10 with 3. So in theory it's possible. How would I do this algorithmically where the number is unknown or is a variable? Okay, let's try 10 is equal to 5. So yeah, equals 5. Max time is going to be 11. So it's 10 plus 1, 9 plus 2, 5 plus 6. Okay, that's just too simple. Let's say n is equal to, so I can't do n equals 10, that's just stupid. N equals, I guess I need to make it bigger still. N equals 6. Max time is 54. This is 9. So 10, 9 plus 2. No, 10, 9, 8 plus 1, 7 plus 2. Interesting. Uh, 7, 6 plus 3, 5 plus 4. So if I have a guess as to the max time, then I can do a check or if it's possible by trying to do the allocation and just going over the battery charges. Each battery charge that is bigger than the max time is going to be just allocated to that computer. And then each battery charge that is less than the max time will use the smallest charge possible. Smallest charge possible. Wonder if I can break up a small charge that's not fully optimized. So what if it was like there were 2 8s and what if the batteries was, let's say, 2 8 8. So, and the n is here is just 2. In theory here, max time is 9. Max time is 9. So I would say 8 gets assigned 2. It doesn't fully use up the 2. It puts back a 1. Or maybe it replaces the 2 with a 1. And then the next 8 takes the other 1. Is that always going to be feasible to split up a charge in that fashion? I think it might. So then if it doesn't work, then I just return false for that possible check. Okay, so maybe this is binary search for the correct value. So in general for binary search, I always want a is possible function, taking in some possible value that I'm checking for. So so I guess I am checking for max time here, but this is the, I guess they call this the is possible for this max time. What do I need to know here? Um, so batteries can be sorted. But I think it's fine. So I think I need 2 pointers, one for the index of the back and one for the index of the front. Back being kind of where the battery starts charging at, and the front is kind of the small values that it uses it to fill up the remainder. I'm going to do this so that the battery's array doesn't get messed with. I guess I can have, okay, I think I have like a remainder. I don't think I have a spare. Let's say count as 0. Then it should be something like return false or return true in here, and there's going to be a for loop that returns false. I think this should be for every B index in the length of batteries. B length is going to be the length of batteries. Every battery index in the range of B length. Right. I think one. Yeah, do I want this? Should batteries be backwards sorted? Do need 2 pointers. Okay, I think this should probably be backwards. Okay, sort reverse equals true. Okay, so maybe it should be like this. So then the start charge is going to be equal to batteries at this index. So this is the baseline. If the start charge is maybe this should be whatever. I guess maybe this should be in the range of actually this should be in the range of n, because I only care about n batteries or n computers being charged. But this is an index. And this does still. So 2, 2, 3, 3. Okay, so let's do this example here. So 3, 3, 3. So n is 2. Max charge is 4. So what's going to happen is it's going to say 3 is less than 4. Then it's less than 4. Then how much is it going to use? It's going to use up all 3. And then it's going to take 1 away from this thing and put 2 back here. take one away from this thing to put two back here. And then this thing also takes 3 here, takes 3, and then uses one of the 2 spare. I think that's... Is that always workable? Is there ever a chance where... Yeah, I think that should always be working. Okay, so spares can be 0, count is 0. Guess they don't need count actually. Count is implied with the B index. So start charge for this battery, for this computer is going to be the initially high nth largest charge battery. And if this start charge is greater than max time, greater than or equal to max time, then I'm checking for then I need to just continue. Like if I'm checking if the 2 batteries can be charged for 3 minutes and the charge is already 3, then I can just assign it. Or the charge is 5, I'm checking for 3, then it's fine. So I just assign this computer to this battery, and that's going to be kind of perfect. You can't optimize better than that. Else what's going to happen, they're going to use the smallest battery possible, or break up the small battery. Let's break up the smallest battery available. Okay, let's say spare is 0, and I think I'll say the spare index is currently spare index is currently at, I guess it's B, it's B length. It's actually past the end of the array. So need to charge from extra spare batteries. So this could require multiple spares, just using the smallest ones first. So I think this should be something like while, so let's start with deficit, how much I need. So this can be max time minus I think this would be charge actually, not just start charge. So max time minus charge. So that needs to be done by the spares. So I think maybe I can do spare deficit. If deficit, I guess if spare is greater than 0, then deficit is subtracted by whatever the spare currently is. Else, this might be too much, huh? Yeah, this might be too much. If the spare is like 5 and the deficit's only 2, then I just want to make the spare 3. I think there should be deficit minus equals the minimum of deficit and spare. And similarly, spare is going to decrease by that amount. But then this needs to be done multiple times if necessary. So maybe while deficit, this might need to be in a while loop here. While there is a deficit. And it needs to maybe actually while deficit greater than 0 and spare index is still greater than or greater than spare index is still greater than the battery index. It can't equal the spare index can't be hitting the battery index. Alright, keep on. So deficit. So deficit decreases by the minimum deficit. Spare also decreases by the same amount. The decrease, I guess I'll do decrease is equal to this thing. Deficit decreases by that decrease, and the spare decreases by decrease. Okay. So if that's perfect, then if the deficit's 5 and the spare has 5 charge, then they're both going to go to 0. And that breaks this loop. But then I think here, I think I should say if the spare is equal to 0, then I need to move on to the next index, maybe. I do this before or after? I think maybe I need to do this before. If there is no spare charge, then the spare charge is going to be move the index where I find a spare, and then batteries, spare amount is going to equal batteries at this index. Okay. Yes, should this be greater than b index plus 1? Because it can't equal it right here. I guess it should be if spares equal 0 and actually spare equals 0 and here like I can't move on to the battery index. Spare decrements. Guess I can do a check here. Is this saying return false? Okay. Alright, I gotta take a break here. Alright. Try to finish this thing here. So spare is going to be 0. Spare index is going to be from the back of the array. Charge is the battery at this index. If it's perfect, then it's perfect. Next, from spare batteries, spare smallest spare batteries. So the deficit is what's necessary while it's greater than 0, and the spare index is not the same thing as the current index. I think it should, no, this probably needs to be afterwards. Like, should be here. No, what am I doing? Spare index is, if the spare amount is 0, move it. If now, I wonder if I can do this. I wonder if I should check this after the while loop. Yeah, I'll check it after the while loop. Spare index, I guess this could now be, spare index is less than or equal to. Guess that doesn't make sense. Where do I want to check this? It could be that the next time this iterates, no, I guess this is fine. Next time it iterates is going to be, it's going to be in a bad state. The deficit should be even bigger. Yeah, spare index is less than or equal to index. Okay. The spare is 0, move the spare index down 1. No, I guess this just should be, here is fine. So I don't need to wait. But if I don't, do need to check this at some point. No, I guess this here is fine. Okay, spare index. Move to the front. Spare becomes whatever the battery charge is. Otherwise, decrease it. Deficit decreases, spare amount decreases. I think this is too many variables. I think maybe while charge is less than max, while charge is less than max time. Yeah. Let's just get this. Okay, so let's go ahead and just try this. Return, let's say print, so it is possible. Let's do some examples here. Is possible 13 and 14. So 13 should be possible. 14 should not be possible. And it'll be 1 through 10, n is 4. Okay, and I'll just return 0 here. Possible 14 isn't. Okay, so I think the function works in theory. I'll do, say, 12 and 15 just to make sure. Maybe I should do something more exact here. Say n is 5. Yeah, actually n is 5, 11, and 12. This is definitely just right on the cusp of being possible and not possible. This should be true, false. Okay. I guess I should try this one. This should be, it's possible to do 4, but not 5. True, false, hopefully here. Okay, looks like it's working as intended, or it's definitely returning as intended. So here's the binary search. So what is the theoretical, this is theoretical high. We can't really go higher than this. The low would be the minimum. Low might be 1. No, I guess the low would be the minimum of all the values in the array. Right, because there's at least n values. I guess I don't need to search for it if I already reverse sorted it. So it'd be batteries at -1. Okay, so binary search for the maximum possible charge time. So while low is less than high, the mid value is low plus high divided by 2. The return value is going to be the search if this is possible. If that is possible, then you want to try a higher charge time. So then you want to bump up the low. So low equals mid or mid plus 1. I think it should be mid plus 1 because the average is going to be, the average here is going to be rounded down, so you want the higher value. So low could technically be equal to mid. So therefore you want to make sure that it's higher than mid. Else you'll need to lower the high value. So high is equal to mid. And I think you want to return So this should stop when low and high are the same, so I think you should just return low minus 1. It stops when it's too high. So then the last correct, the highest possible thing is going to be low minus 1. Okay. Oh, shucks. Turns 3 expects 4. Really? What is that? It looks like it should return low. Looks like it should return low. So mid. Possible, then it bumps up to mid. Or bumps up to mid plus 1. Okay. Rather than try to figure out just mentally, I'll just go ahead and do some printouts here. Low, high, mid. Shucks. Turn value. So 3, 4, 3. 3, 4, 3. True. So it's possible to do 3. So then it goes to 4. Low equals high at 4, right? So low and high are 4. And actually it would be possible to do 3, 3. Oh, it can be possible to do this thing, I see. So I think highs should be out of bounds, actually. High should be in the actual impossible range, so I think it should be... I could do some batteries divided by n plus 1. That would force it to be impossible. Yeah. Is there a better way of doing that? This is the lowest lowest charge time. Okay. See how this performs. I think. Yeah. It's pretty darn low, isn't it? Ooh. This means there's a linear solution. This means it's just a very slow solution. I mean, this is probably on the order, it's on the same order of magnitude in terms of n log n, I think. So there's a linear solution. Linear, no, it can't possibly be linear. There has to be some sorting. Right? There has to be some sorting. 47 milliseconds. Wonder. If I need to actually. I wonder if the answer is just like in a bounded range of like the average or the average plus 1. I guess it can't be in that bounded range because there's some values that are bigger. There could be values that there's some batteries that are larger. You know what? Oh, I wonder. I wonder if it isn't something quite simple in terms of just mathematically being the sum of the battery charges divided by n. Okay, I feel like this is implying that there's just a linear solution. Linear solution means that you should just look at the thing, look at the array, and somehow there's some sort of greedy approach to it, or some sort of greedy, like you can just look at the value and somehow figure out how to use this value. The max time is the max time, like in terms of having a high limit that is the sum of the batteries divided by n. Just that's theoretical. There's just no way that it's higher than that. So if you look at every battery, if the battery is the utilization of that battery is going to be up to that value, up to this max high value, and then you just sum up those parts. Yeah, that's probably it, actually. Okay, high usage is equal to the sum of all the batteries divided by n. Like there's just no way that you can ever use the battery more than that. Yeah, there's no way that you use it more than that. But then how much do you use every battery? Is it possible that so if you have a bunch of stuff that is less than the high usage, every value in your thing is less than the high usage, then you would return. So the high usage is on average 10, but there's some batteries that are bigger than 10. Let's say there's a battery that's 100 charge. So you're not actually going to get 90 of that 100 because that's just not, there's no time that those 90 can be used. So then you would actually sum up the stuff that's below 10. Not quite, because then you would actually it would be 10 plus a bunch of spare change. Low 10. And then that would be divided by n. So I guess, what does that mean? So let's say this was something like batteries equals 1, 2, 3, 4, and 100. Let's say n is 4, n is 5. So in theory here, let's just do something simpler. N is 4 maybe. Let's do n equals 5. Then obviously it's going to be 1 equals 4. Here the sum is 110. Max time should be 110 divided by 4. 20, 27, 25 plus 2.5, 27.5. So you see 27. You see 100. So the 100 definitely doesn't work. So it's definitely not going to be able to do 100. So you lower this to be 27. And then you recalculate the sum. So it's now, the sum is now 37. And the max time based on that is going to be 9. Then you say here, well, 27 is still bigger than 9. So you need to recompute that. So make this into, so you make this 100 to 27. Max time is still a bit too big, so then make this into a 9. And max time is going to be 37, 19 divided by 4. That's going to be 4. And now it works because this thing is bigger than 4. No, that still doesn't work, does it? Why does it work? Why doesn't it work? Interesting. Just keep on shrinking everything. I think maybe it could be something where if I think about the sum of the spares, sum of spare batteries, where spare battery is a battery that didn't reach the full charge time that is being considered. sum of spare batteries. What's the formula here? Okay, n times the max time is equal to the total charge. N times the max time is equal to total charge is going to be equal to charge from spare batteries plus charge from batteries bigger than spare times the number, no, it's actually charge. It's equal to n times the max charge. Well, max charge is max time. Max charge that I'm considering. This is going to be max charge times the number of batteries greater than or equal to that charge. Okay. The batteries greater than or equal to that max charge. Can I work with this? So say batteries is equal to 2 and batteries is equal to 333. Maybe I can do some sort of prefix sum here. Prefix sum is going to be 0369. Maybe it's too hard of an example. N equals 2, let's say batteries is equal to 1, 2, 3, 4, 1, 2, 3, 4, 5. So in theory I can do 7, like 5, 2, 3, 4. So in theory I can do 7. So I can do, yeah, if I add them all up, divide by n, and that still is bigger than, that's still just bigger than the highest value in the networks. Because there should be some arrangement where that's just allocated perfectly. Maybe I need to do it backwards. Let's say it's actually 10, 5, 4, 3, 2, 1. So here in theory it's going to be 25, 12. 12 is the max. That still works. Okay, I need bigger. So here this adds up to, let's say it adds it to 30. So in theory it could be 15. 15. So the best you can do here is going to be, should be 10 as the charge. What was it before here? There was 12. Interesting. So here the answer should be 15. 20 plus 15 is 35. In theory, it can do 17. if you just do sum of all the values divided by 2. And here it's actually 15 because what you're doing is you're using a cap on this value. The cap on this value is based on the number of values that are bigger than, fuck, this is sorting again. This is sorting again. Oh. But this is a pretty fast thing though. So the number of values before this thing is going to be fully charged batteries that you don't really care about. And then the number of charges after this thing needs to add up to a number that divides into the remaining computers. So maybe I can do okay. So I think I do something like batteries.sort reverse true. Let's say total currently is 0 for every index in range n. I think it should be n, yeah. So first thing is actually I think it should be current. Total should be starting with everything. So let's assume that I try like the 5, 4, 3, 2, 1 array, and there's going to be like 2 batteries or 2 computers for it, so that should be 7. So if the division of total minus current, so total minus current is the sum of the remaining. Let's say the remaining sum is going to be total minus current. If the remaining sum divided by n is bigger than or equal to the value of this index, then that means that everything after here is fine to be optimized in some way to get to this thing. So I think I'd say return the remaining divided by n. Otherwise, I think current increments by the value of this index. I think it should be returned divided by the remaining values, the remaining stuff, so it should be n minus index. So on the most basic case, everything adds up to a value where if you divide it, if all the charges add up to some value like this, right? All your charges add up to a value where if you divide it evenly amongst the n computers, that charge time is bigger than the highest battery charge time, then there's some kind of optimal allocation of those batteries that will make that work. But if it doesn't, like here, the average here is going to be 27. Trigger. Actually, that's not going to work yet. 27. If the batteries at this index is bigger than this thing, now this should be the other way around. No, if the average is bigger than this thing, here the average is smaller than it. So 27 is smaller than this thing. But yeah, so then that means you can't use that whole thing. So you remove that battery from your current total, and then you look at the remaining ones after this. Yeah, I think this should work in all cases. Okay. Okay. Interesting. I guess you did have to sort it. I guess sorting it was faster than I expected. Okay. Well, what was my previous submission for this? Last September, 43 seconds. And then I did November. Somehow the runtime of 43 seconds was actually 6.4. I did binary search back then. Wonder if this was a contest problem. Well, I did this multiple times. Anyways, okay. I wonder if there was like smaller test cases back then. I guess it has the same number of test cases. Anyways, okay. Not sure. Okay, so I guess here, what's the summary for this thing? This is more, I guess, above kind of solution is kind of a math/logic problem. So given the sorted or kind of reverse sorted array of battery charges, the theoretical highest time would be the sum of the batteries divided by n. So for example, let's say you have n equals 2, batteries is 1, 2, 3, 4. Sum is equal to 10. 10 divided by 2 equals 5 is max time. In general, or this will work, well, this will always work if the max time is higher than the is greater than or equal to highest single battery charge. In this case it is, because 5 is greater than 4. However, this doesn't work if that's not true. So for example, n equals 2, batteries is equal to, let's do something simple, 1 and 10, or 1 and 9. Sum is 10. 10 divided by 2 is 5 is max time. But obviously can't do this. Like, you can only charge one thing with the first battery and then you're stuck. So the batteries that are lower, batteries with charges lower than the max time should be only considered to charge the remaining batteries, remaining computers not lucky enough to get the batteries that are assured to last. So for example, let's say you had the first modification of the first, let's say n is equal to 4, and you had batteries that were equal to 1, 2, 3, 4, 1,000, 1,000. The 1,000 charged batteries go to the first 2 laptops, and the remaining kind of spare batteries need to charge the final 2 laptops. So that's what's going on here. So you have some batteries, there's some remaining total. If that remaining total is kind of adequate in the sense that all the battery charges are smaller than that value, then it can be optimized to work. And otherwise, you remove this battery from consideration, and this battery, whatever it is, this high battery amount is going to be higher than whatever you end up using for your average. So, that's the logic. Do a reverse sort on the batteries, keep track of total charges, ignore charges that are impossibly high, or higher than the average, and remove those laptops from being needed to be charged. So yeah, like 1,000, that's gonna be higher than the average, and so you're not gonna use those things, and you're not gonna worry about those laptops. So then you have 4 remaining charges for 2 batteries, or 4 remaining charges for the remaining 2 laptops. Time flexibly O of n log n in order to sort the batteries array and determine and O of n to go through sorted array to determine the optimum charge time. And then space flexi to O of 1, since sorting is in place and no other data structure is needed. Okay.